Hello, and welcome to the course Applied Statistics Using Programming. This is a short video lecture series, and this is the first in that series of videos. In this series of videos, we're going to be talking about statistics in a more practical sense, and we will be looking at how to use it using programming, specifically using R programming. I am Dr. Ian, and this is the first video in that series. So let's get started. In today's video, we're just going to introduce some basic concepts in statistics, and I really want to show why understanding statistics is so important for everyday decision making. This will give an overview of what we might talk about through this course, what you might hope to learn through this short lecture series. So this is lesson 1, where we will just cover the basics of what to expect from this course and some interesting examples of how statistics can help you make better decisions in life, in business, etc. So the textbook for this course is Applied Statistics in Business and Economics. Particularly, I'm using the 7th edition. You may use different editions, but I would highly recommend this textbook series. While it's obviously not written by me, it gives a lot of really in-depth detail and good explanations of a lot of the concepts that we're covering. So using this textbook as a base, I'm going to solve a lot of the problems in the textbook using R rather than Excel. While the textbook will give you examples using Excel, this course is showing how to use R to solve basic problems in statistics. I hope this will give you a better understanding of the base of statistics, whether you are a student or a company worker or simply a researcher or someone interested in statistics. I'm planning this course to be taught at a level that's an introductory level for those who have never used programming and who have never really looked at statistics in depth as well. So the programming language that we use is R programming. I find that R is much easier for beginners to learn. While I would also recommend Python, this course is going to focus on using R to solve a lot of the problems and to use it as a tool for using statistics. So let's get started. There are 3 pillars to this course. One is statistical theory, the base of statistics. The second is applying that theory to real-life examples. Most of the examples given in this course are related to business, but you can understand how they could be used for other social sciences or other fields of research. The third pillar is programming. This course approaches programming at a very basic level. So I'm expecting that you probably don't have any experience, or maybe you don't have much experience programming. If you do, this part will be much easier, but you don't need to have any experience programming to be able to learn from these lecture series. So what does this course actually cover? Students will learn basic research analysis that is useful for applying statistics to many different fields. The course covers various analysis methods and provides actual data to practice the analysis methods. Some of that data comes from the textbook, some of the data has been made by me. The methods covered in the class are basic statistical analysis, regression analysis, analysis of variance, and many other statistical methods we will cover in this course. Course topics can be categorized into 3 parts. Data description, meaning what types of data, what is your sample size, the distribution of the data, and so on. Understanding this data helps us make better decisions and understand the limitations of what we can and cannot explain using statistics. Modeling. How can we make a model to predict or describe the data that we have better? And finally, visualization or interpretation of the results. What is the meaning of the model? What is the meaning of the data? What can we infer from that data? So this is one of my favorite catchphrases. Statistics is not just a science, but it is an art too. What does that mean? Well, statistics is a tool, a scientific tool that is quantitative. However, to really be able to use that tool well, we need to understand the limitations of what that tool can and cannot do. So there's an art to it, and that art comes from experience, experiencing what you should or should not be doing. So statistics can help us make better decisions, even when it might not be intuitive. Let's look at an example. This is a very famous example, and it's been around for quite some time. So this is the Monty Hall problem. So let's go through the Monty Hall problem. Let's say that you are on a game show and you're given the choice of 3 different doors. Behind one door is a car. Behind the other 2 doors are something not very useful. Let's just say those are empty doors. Okay, so behind one of these 3 doors is a car. Behind the other 2 doors is nothing. Which door should you choose? Well, let's say that you chose door 1. It doesn't matter if you chose door 2 or door 3. Let's say you chose one of the doors. I'm going to choose door 1. And after I choose that door, the host of the game show opens another door. In this example, let's say he opened door number 2. The host knows what's behind all the doors, and he opens one of the empty doors. And he asks, do you want to switch the doors to the unopened door? In other words, you chose door 1. Would you like to switch to door 3, or do you want to stick with your choice, door 1? Let's think about this statistically. What is the probability of winning the car if you stay at the door that you chose, door number 1? What is the probability of winning the car by switching to the other door, door number 3 in this case? There are many ways to solve this problem statistically, but I want you to think about it or maybe write it down. What do you think is the probability for number 1? What is the probability for switching to door number 3? All right? Okay, so how can we solve this? The easiest way that I can think of to think about and solve this problem is to think about all of the possible outcomes to this problem. Let's say we picked door number 1. There are 3 possibilities. Either the car is behind door number 1 and we chose the correct door, or it's behind door number 2 and we chose the wrong door, or it's behind door number 3 and we also chose the wrong door. If it's possibility A and we chose the right door, we have a 1/3 chance of picking the correct door the first time, right? There's 3 options. We chose one door. Obviously, if it's random, then we have a 1/3 chance, a 33% chance of getting it right. But that's the easy one. What about if we switch? Well, because the host of the game show knows which doors are empty, he's always going to open an empty door. Now, in possibility A, it doesn't matter which door he opens because we already picked the correct answer. But in possibility B, he would open the empty door where there's no car, and if we switch, we would be switching to the one with the car. Possibility C, the same thing happens. He opens a door that there's nothing behind, so if we switch, we would end up with the door. So because the host knows where the car is, he's not opening a door at random, and this affects the possibility. So it changes the probability by opening an empty door, because if we stay, still there's a 1/3 chance, but if we switch, there's a 2/3 chance that we'll win the car if we switch. So what should we do? we should switch the doors. Why? The probability of winning the car by staying is 33%. By switching to door 3, we would win 66% of the time about. So what is statistics? Statistics is the science of collecting, organizing, analyzing, interpreting, and presenting data. It's a tool that we can use to better understand data or probability in a situation that might be difficult, like this situation that we were just given with the Monty Hall problem. A statistic is a single measure reported as a number used to summarize a sample data set. So for example, the average height of students in Sogang University would be a statistic. What's the difference? Statistics is a field of study. A statistic is a single number that summarizes some data. For example, the average height. There are two primary kinds of statistics. Statistics, the field of study, is capitalized to show that it's a field of study. So there's two different types. The first is descriptive statistics. This refers to the collection, presentation, and summary of data using charts, graphs, or numerical summary, quantitative summary. In other words, descriptive statistics is summarizing your data, describing the data that you have. Inferential statistics, the other type of statistics, refers to the generalizing from a sample to a population, estimating unknown population parameters, drawing conclusions, and making decisions. What does this mean? It means if we have uncertainty, we can infer using statistics to predict what our data might look like. So for example, we might predict what is the average height of students. It's not something easy to calculate. We might infer how many students we might have tomorrow. Inferential statistics also has to do with prediction of some future events, something we might not know, drawing conclusions. So here is a summary of types of statistics. Roughly, this is what we're going to cover throughout this course. Collecting and describing data involves sampling, surveys, visualizing the data, summarizing it numerically, probability models. And next, the second half of this course, we will be making inferences from samples. What is a sample? A sample is getting some data and then making some interpretation about where that sample came from. What is the bigger population? This involves estimating parameters, testing hypotheses, regression and understanding trends from that data, and quality control we probably won't get to through this short course, but it would also be part of making inferences from statistics. So statistics is an essential part of critical thinking because it allows us to test an idea against empirical evidence. So empirical data represents data collected through observation and experiments. Statistical tools are used to compare prior ideas with empirical data. In other words, what we expect to happen versus the actual data that we have. But there are a few things to be careful of. So let's talk about those. So what are the pitfalls? What should we be careful of when we're using statistics? The first one is making a conclusion from a small sample. So be careful about generalizing if you have a small amount of data. For example, if you have a group tour of 10 customers who show increased satisfaction, does that tell us much about the overall tour company? Well, it's a small sample. We shouldn't make that kind of inference. Another example is making conclusions from non-random samples. Be careful about making generalizations from a small special group. Let's look at an example. Humans have a really difficult time understanding when something is random and when it is not. Here are two examples. In one of these examples, in one of these pictures, the dots are placed completely randomly. In the other picture, the dots are not random. Which one of these do you think is the randomized dots, and which one do you think is the non-random dots? There's a pattern to it. Now, most of you probably thought number 1 is the random case. Is that right? That's wrong. Why? In number 1, an algorithm was used to place the dots randomly, but if they were too close to each other, that algorithm would move them apart. In other words, in number 1, they're not completely random. If 2 points were placed too close to each other, they were separated and moved apart. So number 1 is not random. Number 2 is completely random. Many of us have difficulty because we try to make patterns even when there are none. Number 2 was created with a completely random algorithm. Here's another example of why it's difficult to understand and how we can make better decisions based on random data or non-random data. So in this example, this is another very famous case. Many of you have probably heard of this. If not, let's think about it. So the example is, in World War II, Allied bombers came back and they need more armor. The armor is too heavy to put everywhere on the bottom of the plane, so they want to put armor where it will best serve the pilots. So here's the data that they have. This is a real case. So based on the planes that came back, these are all the areas hit by bullets. So someone surveyed the airplane bombers coming back, and they bomb a target, they come back, and looking at where the bullet holes were, these are the airplanes that came back. So which areas should we put armor? Should we put armor where there's bullet holes, or should we put more armor where there's not? Think about it. Well, if the planes that were hit here came back to the base, that means that the planes that were hit in the other places probably didn't come back. So where should we put the armor? We should probably put more armor in the orange areas, the engine, the middle of the wing, the tail, because if the bombers got hit here, they were less likely to return. Therefore, we should armor those areas so that planes that get hit there are okay to come back. Okay. This is an example of data missing not at random. Missing not at random means the data that we have isn't totally random. We only have it from our survivors. So there's a survivorship bias. The surviving airplanes is the only data that we have. The data from the airplanes that crashed, we don't know where they were hit. How is this useful to us? What is the probability of asking a repeat customer versus asking an unsatisfied customer? Let's say you were doing a survey of customers in a restaurant, and you wanted to know, how do they feel about the food? Well, who are you more likely to survey? Are you more likely to survey an unsatisfied customer, or are you more likely to be surveying a repeat customer, someone who likes the food? My guess is unsatisfied customers will probably not come back to the restaurant, and over time, you might end up with more repeat customers rather than unsatisfied customers. So when you're surveying those people in the restaurant, what is the likelihood that they're a repeat or an unsatisfied customer? The probability might not be the same. Pitfall number 3, conclusions from rare events. So some things happen very rarely, and the problem is it might not be surprising when we look at the entire population. Let's look at 2 examples. One common example is asking someone who's very old, how did you get so old? What do you do? What are the tips that keep you alive for so long? Well, How do we know that those same tips that end up with the oldest person, how do we know that many people are not doing the same things and just dying? So again, we have a survivorship bias in this example. Here's another example. This happens very often when somebody wins a really big jackpot, wins a big lottery. What I've seen many times is that the news always goes up and interviews that person, right? And they ask, how did you know? Did you know that you were going to win the lottery? Or what did you do? Did you have any idea? And usually those people say the same thing. I knew I was going to win. I woke up and I knew that I was going to win the jackpot. Well, what about all those people who woke up thinking they were going to win and didn't win, right? Looking at a rare event, someone who lived really long, or winning a jackpot, that happens to very few people, okay? So we need to be careful when inferring from this data. Pitfall number 4, poor survey methods. In many cases, you might get data and analyze that data, but if that data was not sampled properly, then the quality of the data is very low. We shouldn't use low quality data to make inferences or descriptions of a sample or a population, because if that data is not high quality, the output is also not high quality. We call that garbage in, garbage out. If you're using garbage data, you're going to get a garbage conclusion. Okay, so be careful. One of the most common pitfalls, mistakes that people make, is assuming a causal link, a cause and effect, when there is none. So be careful about drawing conclusions when there is no cause and effect link. For example, the Sports Illustrated curse. This is a very famous example as well. Many players do not want to be on the cover of Sports Illustrated magazine because they worry about the curse. Sports Illustrated, a very popular magazine for sports in the United States and internationally as well, they actually acknowledged this curse and made a cover that said, the cover that no one would pose for, right? The Sports Illustrated jinx is what some people would call it. So many of the athletes might be scared because being on the cover causes bad luck in the next season. Why? The athletes who appear on the cover of Sports Illustrated magazine would usually get injured or have poor performance the following season. So many people thought maybe it's because they were on the cover of Sports Illustrated that is causing a curse for their performance in the next season. Why do athletes get selected for the cover? Well, they get selected when they're doing really well. When do athletes get selected for the cover? Well, when they've just had a really good season. How long are athletes the best in their game? Well, if they're doing really well, they generally are not doing really well for a long period of time. Some sports are longer, like baseball, people might perform well for a longer period of time, a few years. And other sports like football, soccer, tennis, it's very difficult to be very good for a very long period of time. So what happens is when they're on the cover of Sports Illustrated magazine, they're doing the best and they can't sustain that performance for a long period of time, so the next season they generally drop in their performance, naturally. So the cause of them performing poorly isn't because they were on the cover. The cause of them being lower is that they're generally regressing toward the mean. Their performance is going back to a more average level. So let's say, for example, a company has the highest stock price. Is that a good time to invest? Is it going to continue going up? This is an example of inferring a causal relationship, a cause and effect, when there might not be one. There's just a correlation. Let's look at another pitfall, generalizing to individuals. Avoid reading too much into generalizations. So for example, a common one might be that men are taller than women. On average, this is true in a statistical sense, but obviously there are many women who are taller than men. This also happens on a cultural basis, right? So I'm a foreigner in Korea. Many older people, particularly, think that foreigners don't like spicy food in general. So they might generalize to me, an individual, and say, oh, you won't like this, it's spicy, right? That's generalizing a statistic, a generalization to an individual. We shouldn't do that. Unconscious bias. Be careful about unconsciously or subtly allowing bias to affect your handling of data. Here's a famous example in social science. There are some countries where people are much more likely to donate their organs. So when people die, maybe in a car crash suddenly, what happens to their organs? Do they get donated to somebody else who needs them or not? Well, in some countries, the rate of donation is much higher than in other countries. So why is this? The percentage of drivers who donate their organs is very different between these European countries. Is this because people in those countries are more selfish than in other countries? Well, it turns out it actually comes from how people sign up to become an organ donor. In some countries, if you check the box if you want to participate in the organ donor program. Most people don't check the box and end up not joining. Whereas in other countries, you need to check the box if you do not want to participate in the organ donor program. Therefore, many people don't check the box and end up joining. People have a tendency to choose the default option, the option that happens when you make no choice. As researchers or statisticians, we need to be aware of this. Don't assign cause to the wrong reason. If we analyze that statistically, we might see that in some countries, the rate is much higher of organ donation than others. So statistics is a tool that might tell us that, but it doesn't tell us why that is the case. Are ethics important for statistics? Statistics is just a tool, right? But as we mentioned earlier, statistics is not just a science, it's also an art too. The art of statistics is highly influenced by ethics. In other words, practical usage, real usage of statistics and statistical techniques are affected by the ethics of whoever is analyzing that data. We should be very careful that statistics is not just objective. There's many subjective aspects of the researcher that might be affecting the outcome or the interpretation of that data. Okay, so that is where ethics comes in. Ethical standards for data analysis include knowing and following accepted procedures, standard statistical procedures, maintaining data integrity, making sure our data is of high quality, and carrying out accurate calculations, understanding how to use the correct tool for the correct data. All right, so the International Statistical Institute, ISI, has a declaration on professional ethics. From the ISI's ethical principles, there are 12 that, if you go to their website, you can see these explained in much more detail, but I've summarized them here. So consider these as the ethical principles. Which one do you think is most important? Pursuing objectivity, trying to be as objective as possible in your analysis. Clarifying obligations and roles. What should the statistician do? What should the data collectors do? What should the managers who might be making a decision based on that do? Okay, make those roles very clear. Assessing alternatives impartially. One of my colleagues, who's a statistician, told me a story about doing a project with a company. And that company's CEO had a really strong preference for one company logo. And his job was to analyze, what do customers want? So they showed this logo and some other candidate logos to many customers and asked, which logo is best? And the customers overwhelmingly chose logo number 1, but the CEO really liked logo number 2. What should that statistician do? So assessing the alternatives impartially. If he chooses the one that the CEO likes, the CEO might be more likely to work with that statistician in the future. But it's important to consider the alternatives impartially, without subjective opinion, without being influenced by what the manager might want you to do. Number 4, that's also related to conflicting interests. The interests of you as an analyst and the interest of whoever's data you're analyzing might be different. So be careful about how you can deal with these kind of conflicting interests before they actually arrive. Avoiding preempted outcomes is also part of the ethics of statistics. Okay, what does that mean? It means avoid doing something that you already expect the outcome of, be open-minded, assess the alternatives impartially, right? These are all related. Guarding privileged information. This one is a really key point these days when companies have large amounts of private customer data, right? Exhibiting professional competence. Know what is the standard in statistics, in research. We need to know what is expected and what is the best methods. That's part of ethics, being competent at analyzing the data. Maintaining confidence in statistics. If you did the statistics right, trust it. Expose and review methods and findings. So be transparent about your methods, communicate ethical principles. Make sure that other researchers that you're working with also understand that ethics is a big part of statistics. Bearing responsibility for the integrity of the discipline, be responsible for making sure that statistics are done properly and that people understand how it's being done, and protect the interest of your subjects. Make sure that you are not exploiting the subjects where you got the data from. Don't exploit the subject. Okay? These are the 12 ethical principles of the ISI. Did they miss any? Which ones are most important? All right, so that's the end of today's lecture. Today is just a general idea of what is statistics, how can it be used, and what should we be careful of when we use it. The next lesson is going to be a little bit more technical, and we're going to learn a little bit more about what statistical methods to use and how to use those methods using programming. Thank you for listening. This is Dr. Ian coming from Sogong University. Thank you, and hopefully see you in the next video. Hopefully see you in the next video. Bye. So what is statistics? Statistics is the science of collecting, organizing, and analyzing. Let's start again. Statistics is the science of collecting, organizing, and let's start again. How is this useful to us? How is this useful to us? Well, what is the